In this video, we are going to talk about degree of unsaturation. This information is coming from chapter 14, but I found it very useful if you know it while drawing Lewis structures. Drawing Lewis structure can get a little complicated when we talk about drawing double bonds and triple bonds. There is an easy calculation we can do to determine what we call degree of unsaturation here. So if the molecule has all the possible hydrogen atoms, it's a saturated molecule. As soon as we add a ring, a double bond, or triple bond, we call that molecule unsaturated. So if you look at the first structure, C5H12, it is following this formula and it's a saturated molecule. The moment that we add a double bond to that system, we are removing 2 hydrogens from the system. And if we add another bond to make a triple bond, we are removing 2 more hydrogens. So calculation of degree of unsaturation and the number that we can get from that calculation, which is completely easy calculation, can give us very useful information while drawing Lewis structure. If the HDI or degree of unsaturation equals 0, that means we have no rings, double bond or triple bonds in the molecule, so we just all have single bonds. If the HDI equals to 1, that means we should have either a double bond or a ring in the molecule. HDI equals to 2 means that we either have a double bond and a ring together, or a triple bond, or 2 double bonds together, or 2 rings together. So you can guess where that's going. Therefore, knowing these numbers and being able to calculate HDI for a single molecule can give us good information about the saturation status of that molecule. Here is the formula for HDI calculation. So this formula says that we need to do 1/2 of 2 times number of carbon plus 2 plus number of nitrogens minus number of hydrogens in the formula and minus number of halogens. That X means halogens, and halogens are fluorine, chlorine, bromine, and iodine. So for example, as a practice, we want to calculate the HDI for this molecular formula. So we can use the HDI formula 1/2 2 times the number of carbons. We have 5 carbons in this formula, plus 2 plus the number of nitrogens. We have not 1 nitrogen here, minus number of hydrogens, and minus 1, which is the number of halogens. Doing the calculation, you can get the HDI equals 2, and that 2 means we can either have a double bond and a ring, or a triple bond, or 2 double bonds, and based on that we can come up with some structures for the molecule. So for example, possible structures are drawn here. In this one we have a double bond and a ring. In this one we have a triple bond. These 2 structures, they have the same molecular formula but different bond connectivity. So you can guess what is their relationship. They are constitutional isomers. So a few practice problems here. Let's calculate HDI for these molecules. Let me draw the formula one more time. HDI equals 1/2 number of carbon plus 2 plus number of nitrogens minus hydrogens and minus halogens. Okay, so let's calculate HDI for each formula. HDI here equals 1/2. We have 6 carbons, so 2 times 6. We have 2. We don't have any nitrogen, so plus 0. We have 10 hydrogens and 0 halogens. And if you do the math, the HDI here equals to 2. For the second molecule, the HDI, it's going to be equals to 1. And for the third molecule, the HDI is also gonna be 1. A few practice problems here. We want to know how knowing HDI can be helpful while drawing Lewis structure. So especially when you have more than one carbon in a specific molecule, it is always nice that you calculate HDI first. So if I calculate HDI for this molecule, gives me the number of 1. And that 1 means that I either have a double bond or a ring in the molecule. So I know that to make a ring, I need at least 3 carbons. Therefore, the ring cannot be in the molecule. So I'll definitely have a double bond in this molecule. Now let's do the regular 6 steps that we talked about before to draw its Lewis structure. So the first step is to calculate the number of valence electrons. We have 2 carbons here. Each carbon has 4 valence electrons. And we have 4 hydrogens. Each has 1 valence electron. Gives me the total number of 12 valence electrons. The next step is to connect the atoms together in order that we see them. Okay, I can connect 2 carbons together because I can see C2. And then I can see H4. So something very important here is that in chemistry, we love symmetry. So if we can do symmetry for the molecule, we always do that. Meaning that this molecule prefers to have 2 hydrogens on one carbon and 2 hydrogens on another one. All right. Now we need to count how many electrons we use to draw the single bonds. So I use 2, 4, 6, 8, 10 electrons till now. And if I subtract them from number of valence electrons, that gives me 2 remaining electrons. And I put that remaining on one of the carbons. Now we need to check the octet and duet in the molecule. So hydrogens, they have their own duets. They are good. This carbon has 2, 4, 6, 8. This carbon has 2, 4, 6. So it lacks electrons. Therefore, this carbon will share the electron with it. And this is the structure of ethylene that we draw. And this is what we expected. The HDI was 1, meaning that we should have 1 double bond in the molecule, and this structure confirms that. The next structure is C2H2. Again, in the similar step, we calculate HDI, and HDI here would be 2. So that 2 can tell us we either have double bond and ring in the molecule, or a triple bond, or 2 double bonds, or 2 rings. So we know that to draw a ring, we need at least 3 carbons. Therefore, this option is out, and this option is out. All right. Now let's do a regular Lewis structure calculation that we do by counting number of valence electrons first. So I have 2 carbons. Each carbon has 4 valence electrons, and I have 2 hydrogens, which gives me the total number of 10 valence electrons. Then I need to do connectivity. Okay, and as I just told you, we like symmetry in chemistry, so each carbon would get 1 hydrogen. Then we need to count how many electrons we used till now. 2, 4, 6, so minus 10 that we use for single bonds gives me 4 remaining electrons. Now I can put all 4 electrons on a single carbon, and then I need to check basically the octet and duet. So this hydrogen has duet, both of them. This carbon has 2, 4, 6, 8 electrons. It is octet. This carbon has 2, 4, so it lacks electrons. Therefore, this carbon will share the electrons to make both of them octet. And this is what we calculated with the HDI. So HDI2 tells us we could have a triple bond, which is confirmed here. Now the last structure. So something very important about ionic compound is that we cannot calculate HDI for them. So just remember that. So in this case, we need to do our regular Lewis structure procedure, 6 steps that we need to follow without calculation of HDI. So we first need to count the number of valence electrons here. I have 2 carbons. Each carbon has 4 valence electrons and 5 hydrogens. Each has 1 valence electrons. And I have a plus charge, meaning that I need to remove 1 electron. So that gives me 8. This is 5. So overall I would have 12 valence electrons. Now I need to do bond connectivity. So 2 carbons, I can see C2, connect them together. I have 5 hydrogens. So I can put 3 of them on one carbon and 2 of them on the other. I cannot follow symmetry here because I don't have enough number of hydrogens. Then I need to count how many electrons I used to draw the single bonds. So I used 2, 4, 6, 8, 10, 12 electrons. And if I remove that from these 12 electrons, that gives me 0 remaining electrons. Okay. So let's check the octet. This carbon is octet. This carbon is not. All right. So let's do the formal charge calculation here for this carbon. I didn't do formal charge calculation in the other 2 examples because it wasn't needed. The structure was pretty simple. But don't forget, always calculate formal charges. For this carbon, I'm going to do that. So this carbon, and the formula for it, formal charge, number of valence electrons minus number of bonds minus dots. So we have 4 valence electrons for carbon, 3 bonds around it, and 0 dots. That gives me the plus 1 charge. So I put that plus in here. So this plus on this molecular formula belongs to this carbon. And actually without calculation, we can even know that the basically trivalent carbon without any lone pair is always positively charged. We have carbocation.